and organizational leadership within the lighting and electronics industry. She has a strong track record in driving market growth, leading high-performing teams, and launching award-winning LED luminaries across multiple segments. Her expertise spans new product commercialization, strategic planning, and operational excellence. Madam Vasavi holds 3 patents and has published over 15 articles in applied physics letters and other scholarly journals. She earned her BE in Electronics and Communication Engineering from SRKR Engineering College, Bhimavaram, Andhra Pradesh, and an MS in Microelectronics from the University of South Carolina, United States of America, and an MBA in Finance and Services from North Carolina State University. Now, currently, she serves as a Director of Engineering. Thank you so much, madam, for accepting our invitation to deliver a talk to the Kids W students, ma'am. Over to you, ma'am.
Okay. Thank you very much. Thanks, everyone. Uh, I'm very honored to be given this opportunity to speak with the students from Kakatiya Institute of Technology and Science. I'm very excited to be able to present my experience and journey in the LED lighting industry with you all. I understand that students from electronics and communications, electrical engineering, mechanical instrumentation, and civil engineering are part of this talk. Really excited to talk to you folks. With that, I'll get started. I'm going to share my screen now. Please let me know if you're able to see it.
Yes, ma'am.
Okay, all right. So yeah, good evening, everyone. As introduced, my name is Vasavi Mandavilli. Today I'm here to share with you my journey through the LED revolution and how the LEDs are transforming global illumination. A little bit about me. I'm currently working as Director of Engineering at Cree Lighting. Uh, I've been involved with commercializing LED lighting since 2004. And over the years, I've had the opportunity to work with technologies that have literally changed the way the world is lighting up right now. As mentioned, I hold 3 patents in this field, but more importantly, I've had the privilege of seeing lighting evolve from something very functional, display lights in your calculators and other appliances, to something really deeply transformative for energy, sustainability, and the human experience. Outside of work, I love hiking, watching movies, and hanging out with my kids. I have 2 daughters who are in school right now, and their only interest in LED is if it is color changing with remotes, etc. So, a little bit of background about myself. I have done electronics and communications engineering in SRKR Bhimavaram, as mentioned. After that, I've done my master's in semiconductors and microelectronics, and followed it up with an MBA in finance and innovation. And I've been working in the lighting industry for the past 20 plus years, starting my journey as a test engineer slash process development engineer, manufacturing LEDs, and slowly grew to NPI product engineer, and then a project manager, and leading other project managers in the project management office, and then finally an engineering manager. And now I'm currently in the position of running the engineering teams as a director. So let's begin our journey through the LED revolution and what it means for engineers like you from different disciplines. So a brief agenda is what we'll explore is we'll start off with the history of lighting and deep diver into solid state lighting, specifically LEDs, and what makes LEDs so unique and different. We will cover some of the terminology used in lighting, then move into their applications, followed by a closer look at design of luminaires using LED technology and the various disciplines that are needed for light luminaire or LED based design. We'll end that with a quick look at manufacturing, dynamic lighting, and careers in this industry. So this will help give a 360-degree looks from the physics of an LED to the design of luminaires to the industry roles. When uh, when I was in your shoes 25 years back as a student, reference to LED was probably in one of my electronics textbook, as in the diodes chapter on it's a it's a diode that emits light, and that is pretty much it, right? I never knew that my whole career will actually be based on LEDs and how vast and in depth the topic can be. So we'll start with the history of lighting, right? Several centuries back, really fire and candles or lamps made from fire were really the only means of seeing after the sun goes down, right? But after that, later on, there was the gas kerosene lamp that was invented where you can use some fuel to have light. But the issues with of them is they're very low efficiency, generate a lot of heat, and don't last as long. It only lasts as long as the fuel is there or the wax is there, right? So, but the one good thing about those old lighting was they were really good at color rendering. I will talk about what color rendering is in a bit, but it really means how how can you see the real color of an object, and they were really good. You can see the real color of an object using those old technologies. And then later on, at the early 19th century, Thomas Edison, one of our most famous inventors, came along and invented the light bulb, which uses a filament that, when heated to a certain degree through electricity, glows bright. And that comes off in the form of light, right? And that has lasted for a long time. We still use the bulbs that were invented by Edison even now in our daily lives. So it was a little more efficient than our gas lamps and other forms. It had a little more lifetime. It could last maybe a few months to a year, and still had a very good color rendering. Not as good as like the sun or the fire, but still pretty good. And later on in the mid 19th centuries came the fluorescent lights, what we call the tube light. It is in every household pretty much in India. And we've used that, where it uses a slightly different technology, where you have a tube that is coated with phosphor, and there is a gas in that tube, and which, when excited from both sides, emits energy, and that hits the phosphor and gets converted to light, and that's what lights up. So it is a slightly more efficient than our standard light bulb, or the incandescent as we call it. It has a much better lifespan. It lasts for like a few years, but the color rendering, which is an important metric actually, is worse compared to a bulb. What it means is, if you see a red color or some bright or some primary colors, red, blue, green, under a fluorescent lamp, it is going to look much faded than when you would look at it under a normal incandescent lamp. And also, it has these coatings in mercury which are not environmentally safe, and so it's not very recyclable, and hence uh, less useful, or less advantageous to the environment, or more harmful, let's say. And then later on, the fluorescent bulb evolved from our standard tube lights to compact fluorescent lights and other form factors to make it easier to install in a wider base. And then came the new next technology, which is still going, which is the LED technology. The first LED was really invented in 2006, and since then it has really revolutionized the lighting, and we are still in the middle of that revolution. It's continuing to do that. So the good thing with LED is it takes the best of both the technologies, where it has a very high efficiency compared to all older forms that I've just talked about. It has a much longer lifetime. It will last 10, 15, 20 years, and it has a very good color rendering. So it takes really the best of both the worlds. Going to next slide. So let's take a deeper dive into what is an LED. An LED stands for light emitting diode, right? So as you all know, you're engineering students, there's a huge electromagnetic radiation range that goes all the way from gamma rays to, AM and shortwave. And in that whole electromagnetic range, there is a very tiny sliver of radiation which is actually visible to us. It is here in between the UV rays and the infrared rays, which is we call the visible light. It's about goes from about 380, 400 nanometers, which is the wavelength, to almost 650, 700 nanometers, which is the red, right? So it goes from the deep violet or blues to the deep red. That is where how much the visible spectrum lasts. So how is LED, how is light generated from a solid state device? A solid state device is basically a semiconductor that does not have any moving parts. So how you generate light from a semiconductor device is that a semiconductor device has a p side, which a positive side, and an n side, and depending on the distance between those two p and n, it's called the band gap of that semiconductor. And however big the band gap is, you get light corresponding to that wavelength. For example, the wider the band gap of the semiconductor, you will get a smaller wavelength because it is governed by this equation lambda, which is wavelength, equal to hc, which is Planck's constant times speed of light divided by the energy of the band gap or the width of the band gap. So the higher the band gap, the lower the wavelength. And lower wavelength means on the left, which is blue, and higher wavelength means red, which is on the right. So you can increase the band gap of a semiconductor by a process called doping, meaning you introduce impurities into that semiconductor to continue to increase that band gap. So the holes that are in the p side move towards the junction, and the electrons from the n side also moves towards the junction when you excite it with an electric current. And they come when they come to the junction, they jump and recombine by a process called electroluminescence. And depending on the gap that they jump, they create that wavelength of light that is comes out and we see it. So this whole process of conversion is called electroluminescence, and that is how LED light comes out. So since there are no moving parts here, it is more efficient and long lasting. And it is more efficient, sorry, because very less heat is generated. Most of the current that is given is converted into light energy and a little bit into the heat energy, unlike some of the old traditional ways of getting light. And hence it lasts longer because there's not as much heat generated. Also, it does not have any harmful chemicals like mercury or other materials. So it is also environment friendly. So that is the mechanism of how an LED works. So let's talk a little bit about the evolution of LED itself and lighting from LED, right? So when the LED was invented, it was not used in general lighting in our homes, etc. It was used more as displays on, laptops, calculators, and some things like that. So the very beginning is in 1960s. A gentleman named Nick Holonyak Jr. at General Electronics invents the first visible LED, which was red. It was very had very low brightness and really used only as indicators. And in once you went into the 70s and the 80s, they developed the other colors, the red and the yellow LEDs, which were higher brightness using a material called gallium nitride. Gallium nitride is a compound that has a higher band gap and hence allows uh, um, shorter wavelength lights to be visible. So as they improved the material science, gallium arsenide, gallium phosphide, they continued to get higher brightness LEDs that was now used more in displays, signal lights, etc. And the lighting revolution really started once the blue LED was invented. And this was by a gentleman named Shuji Nakamura, who holds the initial patents on the blue LEDs. We got a high brightness blue LED using gallium nitride. And what the blue LED enabled, why it enabled lighting and not just confine it to displays, was because you were able to get white light, which is what we want to use in our homes and industries. So how they got the white light is by two mechanisms. Either by mixing the primary colors, you can mix the red, blue, and green light in different ratios and get white light, right? Uh, so you can use different modulation technologies and mixing technologies to use three independent colored lights and get the white light as a result of it. Or you can take a LED that is the blue LED and coat it with a yellow phosphor and get white light from it. So the picture on this right here is uh, we call it blue converted white, which is it's a blue LED. It's coated with that yellow material on top of the LED chip, which is the phosphor that then generates white light, and then you encapsulate it in a silicone gel called the encapsulant or the lens, which then directs the light out in a certain beam fashion. So these were the two technologies. The blue LED enabled getting white light. And once you got the white light in the early 2000s, it really became viable to use them for general lighting as a bulb in our home, as a street light, as an area light, and different lights. So that is why the LED started in the 1960s, but the LED lighting generation started really in the early 2000s, which is just about when I graduated from my engineering college. And the LEDs were very efficient. They were very small because they're small, compact semiconductor devices, right? Compared to like a filament or a big tube light, etc. So they were compact and they were very long lasting because they had low heat, no mechanical moving parts. So this really drove the adoption in automotive headlights, street lights, home lights, and etc. And that kind of started the LED lighting revolution. And it was also first introduced into LED bulbs that started replacing the incandescent, the light bulb, or the compact fluorescent lights. And from 2010 onwards, now that we had general lighting, we started integrating it with smart systems using sensors or controls to tune the color and also integrate with the IoT. So that is a brief evolution of LED and eventually into LED lighting. So let's talk a little bit about the adoption of LED lighting, right? So when it started early 2000s, 2010s, the LED lighting was very expensive because uh, you had to have clean rooms to manufacture the semiconductor material, fabricate the chips, package it, and then convert it into a light bulb. And that took a lot more than something that's been commercialized early 1900s, like the fluorescents, which were a lot cheaper. So, but with efficiency, with process improvements, and etc., you can see that the cost of the lighting has fallen like from 100 times to now 10 times, and it has become easier to now convert to LED lighting. But not only is the price one of the factor, but also the education and awareness of the total cost of ownership. When I say total cost of ownership, what it means is if you go and buy a normal bulb from the shop, it is probably 10 or 15 rupees. But when you go and try to buy an LED bulb, it's 150 rupees. So a person might be thinking, why do I want to spend 150 rupees when I can get a normal bulb for 10 rupees, right? Because they don't understand the cost of ownership over the life of it. So you can go and buy a normal bulb, but it will only last 1,000 hours. So in versus 25,000 hours. So you may have to use like 20 or 30 bulbs in the same lifetime that one LED bulb is enough. So when you look at it over a 10, 15 years time period, you're spending a lot more money in buying several incandescent or tube lights versus buying one LED bulb or one LED light. So that is one factor of the cost of ownership. The second is because LEDs are so much more efficient, one light bulb uses maybe 60 watts of energy. One tube light uses maybe 15 to 20 watts of energy, whereas one LED light that gives the same amount of illumination and light uses about 8 to 10 watts of energy. So across these 10 years, you're spending a lot more money in electricity and energy compared to the LED light. That is why understanding the total cost of ownership of an LED is important, because even if you spend more money upfront, over the life of its usage, it is a lot cheaper. So that is why in the bottom right, you see this chart where orange is the adoption of the LED light from early 2010s, where it was in the single digits. It is now almost 40 to 50% adoption across the world, globally on the sales. And you can see a corresponding decrease in incandescent and fluorescent lights over the time period. So there is still a lot more um, adoption that needs to happen, but we're almost about 50% LED adoption right now. So let's understand some of the terminology used in lighting because it's important. So one of them is called CCT. Anytime you want to describe a light, you use three basic metrics. One is brightness, which is called the lumens, which is the power of light. Then the other is the color, which is the CCT. What it indicates is the appearance of the light based on the black body temperature in Kelvin. So you can see this picture on the far left. That is 2000 Kelvin. That is the color temperature. It's more yellowish, when you have sunrise. And as you grow through at noon, it is about 5,500 Kelvin, which is the bright white, more like the tube light type of things. And when you go into dawn, you kind of go back into that yellowish light, right? So our standard Edison bulb is very warm, which is 2,000 to 3,000 Kelvin. And our fluorescent is very cool. What it means is the 5,000 to 6,000 Kelvin light. The second important metric is the color rendering index. What it means is how accurately is that light showing the true color of an object. So for example, if you take a red apple and look at, and sun for reference is 100 CRI, right? So anything you look under the sun, you will see the true color of that object. Edison bulb is also very close. It's about 98 to 100 CRI compared to a fluorescent tube light where the CRI is only 70%, meaning if you take that red apple and look at it under a fluorescent light, it is going to look more pinkish or not true red. So when you're using it in retail stores where you're selling clothes or shoes or any such objects where color is important, you don't want to use fluorescent lighting. You want to use either bulbs or LED lighting because you can actually see the real colors. And then lumens, as I mentioned, is the brightness of that light. So those are the three main, there are several metrics, but these are the three main metrics for term light defining a light. So where can LED lighting be used, right? Pretty much everywhere. Anywhere you use light, you can use LED light. So you can use it in parking lots to light up the space. You can use it in schools, hospitals, indoor warehouses, everything. You can use industrial, as I mentioned, warehouses, factories, industries, or retail shops. You use them. You use it in automotive lighting for the displays in the screen, the headlights, etc. You use it on roadways for street lights, and you use it in petroleum gas stations for these are called canopy lights under that canopy. So pretty much anywhere you use light, you can use LED lighting. And here is but the design of that LED lighting is very different. If you're designing a LED light for a street versus an indoor facility like a school or an office or a warehouse or canopy lights. So, and we'll talk through application-based design in just a bit. So here is an example of old technology lighting where you can see a lot of shadows. It seems unsafe, really dark, unlit spaces, etc., and a lot more cost in electricity and energy versus the same space that has been upgraded to LED lighting with controls. So you can see the very less shadows. You feel a lot more safer walking through a space that is on the right or parking your car versus a space that is on the left. And while having this easier light, comfortable light, you're also saving a lot of money. You meet the energy code, so you get discount from the utilities and the government. And you can also use controls to turn off when it is daylight or when there is no cars or when there's a car coming in to turn on. So a lot more advantages and controls you can have. So what it means for India. So this is a chart of LED lighting penetration globally. So at the very bottom is North America. It has had good penetration and it's slowly increasing, not as much, and then followed by Europe. But Asia Pacific and the rest of the world, Asia Pacific is where there's the biggest growth projected in LED lighting because the adoption is not on par with other countries, and there is a lot of scope for LED lighting to grow, and this is in billions of dollars of USD, from where it is right now all the way to 2030 and beyond. It's the entire lighting market is estimated about 170 billion, and Asia Pacific gets about a 50 to 60% share of that projected growth. So that is about the evolution of LEDs and LED lighting. Now I want to move into design of lighting systems and how do you design it for specific applications, whether it's a hospital or whether it's a road, and how do you design for the environment. So this is an example of a street light. You have different sizes for there's a 2-lane road versus a huge highway that has maybe multiple 7 to 8 lanes, different sizes. And a lighting system, once you go into a lighting system, you're now moving from LED, which is a semiconductor chip, to an actual electromechanical system that uses different functional disciplines, where you use mechanics, where you use power electronics, where you use semiconductors, where you used optical technology and control technology, etc. So that is why lighting um, covers a lot of engineering disciplines, and it is very interesting in that way. So we'll go through that. So here is a lighting system. You have this die cast aluminum housing that uses the enclosure to hold all the parts, right? And you have some mechanism to mount it, whether it's on a pole, whether it's on a wall, whether it's on the top of a building, whether it's into a ceiling. You need different mounting mechanisms based on where you want to put the light. Then you have control mechanisms and sensors to how to use the light more effectively. Then this is the board that has all the LEDs in it, which is the lighting chips. Then it you has its drivers on how to provide AC current into the LED chips and get light out of it. And then you have optics. These are optics on where do you want the light to go? You don't want to go in every direction. You want the light to go in the direction and on the task subject that you want to light up, right? So you don't want to lose light going in a 360 angle. If you want to light up the road, you want the light to go onto the road, not into the sky. So optics play a very important role in directing the light where it should go. And then you have some enclosures. You have to protect the light. There is rain, there is sun, there is wind. So you have to be able to protect the light from all the environment factors, right? So you have other mechanical parts to or silicone gaskets, grommets, etc., to protect the light from environmental. Or if you're in a building, it's probably vibrating. There's earthquake protection on all of that. So you need to design a lighting system to withstand that environment in the application it is going. So there are several disciplines of light engineering that is needed to design a light, and I'm going to go through each of that discipline right now. The first one is industrial design. Uh, the main purpose of that is how do you want the light to look nice, right? It's not just a square or a rectangle box that is sitting. There is aerodynamics involved when you're on a road installed on a pole. So you want a certain shape for the air to flow and have less resistance on that light. So there is those principles to be involved. There are, heat sinks where you want to design a heat sink to take the heat away from the LED in a efficient manner and compact. So do you want to have circular shapes, rectangular shapes, these fins? What is the height of those fins? All of those is what the industrial design team or industrial design engineering works on, where they determine how compact should it be, what should the shape of it be, what material should you select, is it aluminum, steel, plastic, polycarbonate, etc. And what should be the colors be, what should the finishes be to prevent against corrosion or moisture, etc., to have long lifetime. And also ergonomic and user interaction. It should be easy to install. If a person is carrying a light up a pole to install, it can be very heavy, right? And they should be able to put the light on the pole and open it and install it. So they have to take care to make sure it's easy to install, easy to maintain. It is accessible. Like if a part goes bad, they should be able to replace a part, whether it's like a driver or a sensor or something. So it should be easy to access, and the interface should be friendly to use, either using like a phone app or a system. And again, use materials that are recyclable, so it's not going into the landfill and not no harmful chemicals, etc. And you should also be compliant because it's an electromechanical device with RoHS, which is no lead or cadmium or those harmful elements, and meet energy efficiency factors, meet safety factors. So that is all done through the industrial design team. The next is the LED design itself, and the LED is like the engine, right? That is the main part of the lighting system. So I'm sorry. Its main function is it converts electrical energy coming from the line into light energy with high efficiency. That determines the color. When I say the color, it's not like the color is black or brown or whatever. It's the color of the light. As I mentioned, the CCT, is it 2000K? Is it warm? Is it cool? Or is it something in between? How bright it is, how reliable it is. And There are several types of chip. There is this regular chip that we use in indicators, what we have seen. Then we have the surface mount diodes where you can phosphor convert, right? This is a cool phosphor, this is a warm phosphor. And then you can also have LED arrays where you have multiple LEDs within this substrate and connected with the specific voltage, current, series, and parallel combinations to give you a whole LED array. You can also have filament based LEDs. So several types of LEDs, and you pick which one based on the application that you're designing to. And you can also choose, are you going to use a phosphor, which is the main technology used for lighting, versus RGB mixing. And you design around how do you have the least thermal resistance, the highest efficiency, highest lumens per watt of energy, and lifetime. What L70 and L90 means is how many hours before the light gets to 70% of what its initial light output is, or 90% of what its initial light output is, right? So those are some metrics governed. And again, the color. So you can design discrete LEDs onto a big printed circuit board, or you can use LED arrays depending on the application. Moving on to the electrical design. Now you need a power supply that converts the AC mains and regulates it into DC to power the LEDs, because you don't provide direct AC current into the LEDs. So you need power electronics drivers, or we call them LED drivers, to make that conversion. And if any voltage sags, voltage interruptions, etc., that happen, to continue to provide DC, or you also have emergency backup EBs as part of the lighting system. So when there is a blackout, that the light can still be on through because of the emergency battery backup. And what the power supply or the driver also does is it allows you to dim the LEDs, right? When it's already too bright, you don't need so much brightness, or when it is daylight, or when there is nobody in the room, it enables dimming and automation to be more energy efficient. And you can integrate protection. So for example, you have lightning strikes outside, you have electromagnetic interference. So you can integrate protection in the form of fuses, surges, or EMI filters to control, to protect your power electronics and also control, right? So the key components are, you have a driver, you can either have constant current or constant voltage, include that have over voltage protection, over temperature protection, uses fuses, etc., to protect your circuit. And you can enhance the design through using dimming systems. You can have an analog dimming system where you can just use the dimmer to go from 100% 10 volts all the way down to 0%. You can have digital dimming through pulse width modulation, or there is a DALI protocol or DMX, etc. You can have sensors for motion. For example, in a warehouse, when there is nobody working, you don't need all the lights on. So there's a motion sensor that when only people are there, or when forklifts are there, the light turns on. Or you can have daylight sensors where if it is daylight, you don't need the street light to be on at 100%. There is the sun that is pretty much lighting it up. So it will turn off, and it will only turn on when a certain percentage of ambient light is reached, and or occupancy, right? You have smart controls where you can remotely monitor if in a mesh or if in a town a light goes off, you can remotely monitor it and send people to just fix that light. You have also communication protocols such as Bluetooth, Wi-Fi, and Zigbee to communicate with this, update your firmware over the air, etc. So that is electrical design, electronics and communications, instrumentation, all of that comes into the design of these drivers. Moving on to optical design, now the important part. So now you have an LED system, you have the driver system that is powering the LED, and the light is coming out. Now, where do you want the light to go, right? So you don't want the light to go everywhere, as I mentioned. So the main purpose of the optical design is to control the shape of the light that is coming out, the direction that it is going in, and the intensity you want. And it can also improve the uniformity and the aesthetic quality of that illumination. What I call bug. Bug stands for B is for brightness, U is for uplight, how much light is going up versus coming down, and G is glare. So go and look at a light bulb in your home, right? It is very bright. You cannot look at it directly for a long time. But go and look at an LED light. You can look at it for a longer time without hurting your eyes because it has a much more uniform light output and very less glare. So that is the function of the optical design, is to provide a uniform light. And you can do it several ways. Our primary optics are, as I mentioned, the encapsulation lens that is on top of the LED chip for basic light. And then secondary optics you have is various lenses, reflectors. Reflector is, to change the direction of the light. A diffuser is to reduce the brightness and make it more uniform and less glary. You can use prisms, baffles, waveguides, some films, etc. So these are some examples of tools you use for designing that optic, right? You can use light tools, which is used for the design of the lens and reflector, or Zmax for beam shaping, Trace Pro for diffusers, and some equipment that is used to measure that light. You use what's called a goniophotometer, which measures the distribution of the light, how it is coming out, and an integrating sphere, which measures the brightness, color, and other light characteristics. So here is a basic diagram of an lighting optical system. You have the LED and you use these secondary lenses or reflectors or diffusers on how you want the light to come out of that system. And these are some of the tools that show you through simulation how that light is going to come out before you actually make the part. So that's optical engineering, which is a subset of mechanical engineering. And then going into the mechanical design itself, which is basically all the parts that hold that light together, right? What does the mechanical parts of it do? Is it provides the structural support, and that is what makes it, durable and long lasting. It takes the heat away from, so there's not as much heat generated as a regular light, but there is still some light, there is still some heat energy generated. And how do you take the heat away from the LED is using these, what we call heat sinks or housings, and the material of which can be, primarily aluminum. That is the best part to take the heat away, and the design of those. It also protects the system from dust, moisture, rain, etc., and impact, right? Like if you throw it down, it shouldn't break. And you should be able to mount it on different types of surfaces, depending on the type, if it's on poles, walls, ceilings, etc. So that is what the purpose of the mechanical system is it enables you to use that light in different application and protects it as well. And then, so key mechanical components, as I said, is heatsink, housing or enclosure, and mounting hardware. And what tools do we use typically for mechanical design? We use SolidWorks, AutoCAD for the 3D modeling, to make the assemblies, to make the drawings. We use software such as ANSYS for simulating thermally. If I put 100 watts of energy into this lighting fixture, what is my temperature spread across it, right? You can see it's hottest where the source of the light is, and as you go away from it, it starts to get cooler. So you have to be able to simulate to make sure your housing is providing a good thermal path. And then there is this COMSOL, which provides a couple both thermal, electrical, and mechanical analysis. Here is a simulation of the structural integrity of this bracket, because when you are mounting your light to a pole, you use very high torque so it doesn't fall off, right? If there's an earthquake or just wind or vibration. So you have to be able to simulate to see that material, the design of that structure can withstand that kind of stresses. Moving on, so now that primarily covers the various engineering disciplines needed to design a lighting system. Like, who would have thought that to design a lighting system, you need 5 to 6 engineering disciplines to come together, right? So finally, now you've designed the parts, you have got them tooled by the suppliers with the right materials and everything. Now you have to assemble this whole system together. You need to put it together. So assembly line manufacturing engineering is also an important discipline to get the end product to the customer. So this is this is a picture of an assembly line as it goes down. You're putting the heat sink, you're assembling, you're screwing it down, you're putting the optics on it, and then you're packaging it, you're testing it at the end to make sure it lights up, that you get the correct power factor, uh, PhD, etc. Right? So there's a whole assembly process and a discipline to make sure you're doing it very efficiently and less scrap, etc. So that is basic lighting system. But now, with the advent of controls and other technologies, uh, lighting has also become a human experience. So this is an example of cadient dynamic lighting. So it's called bringing the outdoors in. So the same light, how can you make sure it mimics the outdoors, right? Because if you're familiar with the circadian rhythm is our body's response 24-hour cycle on how it responds to light and darkness, right? So we have now designed a light that mimics that circadian rhythm of the body for our health and well-being. So I'm going to play a video, and you will see it kind of transition from sunrise to sunset. You may not hear the audio, but I will talk through it. So you can see that it's dark. I'm sorry, I'm going to play it from the beginning. Okay. So you can see this lighting transition from sunrise, where only the east and the panels are illuminated, to noon, where the light is above our heads and the top, and then it transitions into sunset, or the evening time, and then finally into dusk and night. So you can program this. You can program this to work however you want. It is particularly beneficial in hospitals or places where you do not have windows and where the sunlight is not coming in. You can use these kind of lights to kind of feel like you're still sitting in the outdoors. So this is a very complex design that included all of the engineering disciplines. Actually, I forgot to mention even software, or I would say computer engineering, because to design the firmware and the software for the sensors to work is also an important discipline in the design of lighting systems. Uh, Moving on. So what careers can you have in the lighting industry, right? As I mentioned, this is a snapshot, but there's probably more. There is mechanical and optical engineering, LED and electronics engineering. There's computer engineering for software and firmware, industrial design for the look of it, manufacturing for process, quality, industrial, the assembly line setup. Also MBA for working on the supply chain side of things, finance, project management, sales, marketing. And there are also lighting certifications. LC is one of them, which is lighting certified, but there are others as well. So there's a lot of careers that can be made in the lighting industry coming from various engineering disciplines. So that is the end of my presentation. Thank you very much. I will take any questions if there are any. And once again, thank you for the opportunity.
Thank you. Thank you very much, madam, for enlightening the students of Kids Warangal. Now, dear students, it is time for you to ask any question to the expert. So I have enabled the question and answer palette. You can type in that chat box so that madam will see, and I can also see.
Yeah, good evening, madam. I am Dr. Venkateshwar Reddy, Associate
Hello,
Professor
sir.
and Head, Associate Professor and Head Department of ECE. And so we are very much delighted, madam, to listen your lecture on LED. And from the Kids Warangal fraternity, we are very much thankful to you, madam. And Kids Warangal is a 45 years old institution. We are working towards a better society and for creating good opportunity to the students and for good career to the students, madam. And this is a expert talk series. This is designed for exclusively in the revised curriculum under URR 24. We kept this as one of the course. So we are inviting experts from various industries, and so that we can bridge the gap between academics and industry, academics and industries, madam. And we are very much thankful to you, madam. And starting from evolution of LEDs and also the working principle of LED, converting this recombination of electrons and holes into photons, and collection of photons is called as light. And from working principle of LED, and also to optical design and mechanical design, and what are the career opportunity in LEDs, and you have nicely explained, madam. We are very much thankful to you. And from Kids Varangal, we are very much happy to listen this lecture, madam. And our principal
Thank you,
sir.
sir.
Yes,
Thank
madam.
you very much for giving me this opportunity. I was also a student 25 years back, and
Yes,
at that time there was maybe one paragraph on LEDs in our electronics
yes, madam.
textbook. At that time, I
Yes.
didn't realize I will work for 20 years in this industry, and how big and how involved engineering is needed in LEDs and lighting design. So your initiative is really good that you started to introduce the students what they're studying, how it can apply in real life. So I'm very honored for this opportunity and to share my learning experience with the students.
And we are also happy, madam. Your friend, I mean, your classmate, Dr. Chandrasekhar sir, is also one of his colleague, my colleague, madam. We are very also, sir is also coordinating in the various works, madam. We are also very happy. And thank you,
Yes, and
madam.
thank
Thank
you
you
to
for
Chandrasekhar for reaching out and
yes.
giving me this
Chandrasekhar sir.
opportunity. Yes.
Yes. Thank you, madam. Thank you for taking the
Yes,
session.
thank you, sir.
Thank you.
Thank you. Thank you. Can
Dear
I, should
students,
I
Madam,
leave?
Madam, it seems no question has been asked by the students, madam. I hope every student has understand what you have delivered, ma'am. Thank you. Thanks a lot, madam. So, on behalf of all the students and organizers, I extend our heartfelt thanks to you, ma'am, for delivering such an insightful and engaging session on engineering efficiently lighting the world. Your expertise, clarity, and passion have truly inspired us, madam. And thank you once again for taking the time to enlighten us. And we deeply appreciate your contribution and hope to have the opportunity to learn from you again in the future, ma'am. Thanks a lot, ma'am.
Okay, I do see a question. Is there any chance to see infrared rays with naked eye, and up to which wavelength we can see?
Yes, yes.
Actually, normal human eye, we cannot see infrared rays. Typically, we can start seeing red from around 700 nanometers.
Okay, Chanukya, I hope madam has answered your question.
And there's another question, whether LED light is affectable for eyes. So I'm trying to, does it affect your eyes? So yes, if you go too much into the blue, into the ultraviolet, it can be harmful for the eyes. That is why even in glasses or laptops, they are giving what is called the blue light filter. So yes, it can be harmful for the eyes when above a certain wavelength for a longer period of time, and you need to use protection for it. Okay, I think that's all. I don't see any more questions.
Yes, ma'am. Yes, ma'am. No questions are there.
Okay, thank you, sir.
Thank you.
Bye.
Thank you, madam. Thanks a lot.
Good evening. Bye.
Thank you. Now, students, it is the time to write the test. So I hope the link has been already shared in the WhatsApp group and also email. So let me keep the same link here also. Right, so I have shared the link here in the chat box. You can click on the link and you can attempt the test. The time is only up to 10 minutes. Automatically, the link will be disabled. Thank you, Samir sir, Sai Lakshman sir, Srinivas sir, Chandrasekhar sir.
Sir, thank you, sir.
Thank you, Pradeep sir.
Thank you, ma'am.
Sir, morning when you called, I was in the class, sir. Sorry, I forgot to call you
Oh,
again.
okay, no issue, sir.
Thank you, sir.
Thank you, sir. Thanks a lot.